Hello everyone, welcome to physics class. This is our last module from the chapter Light, Reflection and Refraction. In today's module, let us learn the sign convention in spherical lenses, lens formula, power of a lens and the numericals related to spherical lenses and power of a lens. Sign convention for spherical lenses. According to new Cartesian sign convention, all the distances are measured from the optical center of the lens. That means optical center is the origin from where we take the measurements. The distance is measured in the direction of incident light is taken as positive. And the distance measured against the direction of incident light is taken as negative. That means children, object is always placed on the left side of the lens. So the direction of incident light is from left to right. That means if we measure the distance from optical center to the left, it is negative. And if we measure the distance from optical center to the right side of the lens, those distances are positive. Next, the heights measured above the principal axis is taken as positive. And the heights measured downward and perpendicular to principal axis are taken as negative. So based on the new Cartesian sign convention, focal length of a convex lens is considered positive, written with a plus sign, whereas the focal length of a concave lens is considered negative, written with a minus sign. So the sign convention for spherical lenses is very similar to the sign convention for spherical mirrors. So children, what are the conclusions that we can reach on? Object distance u will be negative for both convex and concave lens. Image distance v can be positive or negative for a convex lens. If v is positive, that means image is formed on the right side of the lens or the other side of the lens. If v is negative, image is formed on the left side of the lens or on the same side where we keep the object. For concave lens, v is negative. Because we know concave lens produce virtual images and those images are formed on the same side of the lens where we keep the object. Focal length f of a convex lens is always positive, whereas for a concave lens f is negative. Height of the object is always positive. Height of an image h dash can be positive or negative. It's positive means the image is formed above the principal axis, and if h dash is negative means image is formed below the principal axis. So hope it is clear. Children, we studied a formula for spherical mirrors. So here too, in lenses, we have a formula which gives the relationship between the object distance u, image distance v and focal length f. So this is called as the lens formula and it is written as 1 by v minus 1 by u is equal to 1 by f. Now next is linear magnification noted by the letter small m. Linear magnification, as we know, it is the ratio of the size of the image to the size of the object, that is h dash by h. Or it is also the ratio of the image distance to the object distance. In mirrors, children, you remember the magnification formula for mirrors has a minus sign. But here, the magnification formula for lenses has no minus sign. So we can combine these two equations, that is m is equal to h dash by h is equal to v by u. So if m is negative, that means the image is real and inverted, and if m is positive, the image is virtual and erect. And we know the conditions. If m is equal to 1, the size of the height of the image will be equal to the height of the object. If m is greater than 1, the image will be enlarged. If m is less than 1, the image will be diminished. And also please take a note, the convex lenses can form both enlarged as well as diminished images, whereas a concave lens forms images which are always smaller than the object. Power of a lens noted by the letter capital P. Children, we know that focal length is the distance from the optic center to the principal focus. Look the figure that is shown there. You can see a thin lens and a thick lens. In a thick lens, the light rays are focused onto a point very close to the optic center. There the focal length is less. Whereas in a thin lens, as the focal length is more, the light rays are focused onto a point, or the focus lies a little more far from the optic center. So we can say that the ability of a lens to converge or diverge the light rays depends on its focal length, because here the thick lens converges the light ray faster than the thin lens, and focal length is a factor here. So now what is power? Power of a lens depends on this focal length. So how to define power? Power of a lens is the reciprocal of the focal length of the lens, or we can say it is the degree of convergence or divergence of light rays achieved by a lens. Its SI unit is dioptre, noted by capital D, and equation P in dioptre is equal to 1 by F, and focal length is in meters. So let us define 1 dioptre. 1 dioptre is the power of a lens whose focal length is 1 meter. So we can say a lens of short focal length has more power, whereas a lens of long focal length has less power, because power and focal length are inversely related. Hope children you understood. Power of a convex lens is positive, because focal length of convex lens is positive, so power of a convex lens is positive, and that of a concave lens is negative. When several lenses are placed in contact with one another, the power of the combination of lenses is equal to the algebraic sum of the powers of the individual lenses. That is, P is equal to P1 plus P2 plus P3 plus etc. Please note, a thick lens has short focal length but more power. A thin lens has large focal length but less power. Let us start our numericals. Question number 1. 1/2 of a convex lens is covered with black paper. Will this lens produce a complete image of the object? Verify your answer experimentally. Explain your observations. Children, answer is yes. A complete image will be formed. When 1/2 of the lens, that means lower or upper, is covered, the other half part of the lens will refract the light rays through it, and it will lead to a final image. And the intensity of the image will be reduced to half. So for experimental verification, we can take a convex lens. We can mount it vertically on the optical bench. On one side of the lens, place a needle or a burning candle at 2f1. On the opposite side of the lens, mount a white screen. Take the complete and sharp image of the burning candle on the screen by adjusting the position of the screen, which is obtained at 2f2. So what is the explanation given, which can be given? This is because some of the rays from the number of incident light rays are refracted through the uncovered part of the lens, but other rays are blocked by the covered part of the lens. So the lesser number of refracted rays will now reach on the screen. So the less bright the image will be, but the complete image will be formed. Question number 2. An object 5 cm in length is held 25 cm away from a converging lens of focal length 10 cm. Draw the ray diagram and find the position, size and nature of the image formed. Children, try to draw a ray diagram. Object is kept 25 cm in front of the lens. So, according to sign convention, U will be negative 25 cm. Focal length of the convex lens, we know F will be plus 10 cm. So, we have to find the position of the image. So, we have to calculate image distance V and size of the image. H dash has to be calculated given height of the object H as 5 cm. So, let us use the lens formula. 1 by F is 1 by V minus 1 by U. So, let us substitute. 1 by 10 is equal to 1 by V minus 1 by negative 25. So, it becomes 1 by V is equal to 1 by 10 plus 1 by 25, and hence we take the LCM of 10 and 25, and finally we get V as 50 by 3, that is 16.66, it's recurring centimeter. So what is the position of the image? Image is formed 16.66 centimeter on the other side of the lens, or we can say on the right side of the lens, since V is positive. Let us continue with the second question. Next, to find the size of the image, we will use the equation M is equal to H dash by H is equal to V by U. We know H we know V, U. So let us substitute. H dash by 5 is equal to V. Let us take the fractional value 50 by 3 by negative 25. So we get the H dash as 3.33 centimeter. So children, the size of the object was 5 centimeter, whereas the size of the image is 3.33. So we understand that the image is diminished. So let us confirm. Let us find the magnification. So we know we can take any of the equation, m is equal to h dash by h or m is equal to v by u. So let us substitute. So here let us take h dash by h. So take the fractional value negative 10 by 3, that is our h dash, and h is 5. So when we divide, we get m as negative 0.66. So since m is negative, we understand that it's a real image, and since m is less than 1, we confirm that it's a diminished image. So nature of the image is real and inverted. So hope the numerical is clear. Question number 3. A concave lens of focal length 15 cm forms an image 10 cm from the lens. How far is the object from the lens? Draw the ray diagram. So children, it's a numerical related to concave lens. So focal length of the concave lens, as we know, it's negative. So f is equal to minus 15 cm. Image distance is given there, and since it's a concave lens, we know v is negative 10 cm. We have to find where is the object kept, or we have to find the object distance u. So let us use the lens formula. 1 by f is equal to 1 by v minus 1 by u. When we rearrange, 1 by u is equal to 1 by v minus 1 by f. Let us substitute. 1 by u is equal to 1 by negative 10 minus 1 by negative 15. So finally we get 1 by u is equal to minus 1 by 30. Taking the reciprocal, u is equal to negative 30 centimeter. So hence the object distance is negative 30 centimeter. Here the negative value shows that the object should be placed 30 centimeter in front of the concave lens. Now to draw the ray diagram. So children, please identify where is the object kept. Here the object is kept between infinity and optic center. That is 30 centimeter from the optic center towards the left side. And finally, where is the image formed? The image is formed between optic center and f1. That is 10 centimeter from the optic center. So hope the ray diagram is clear to you. So we have to draw the ray diagram also. Children, next the numericals related to power. Question number 4. Find the focal length of a lens of power negative 2.0 diopter. What type of a lens is this? So children, given power of this lens as negative 2.0 diopter. So to find focal length, we have to use the equation P is equal to 1 by f. So negative 2.0 is equal to 1 by f, or f is equal to 1 by p. So by substituting the values, 1 by negative 2 gives as negative 0.5 meter, and by converting into centimeters, by multiplying by 100, we get focal length as negative 50 centimeter. So since the focal length obtained is negative, we confirm that it is a concave lens. Question number 5. A doctor has prescribed a corrective lens of power plus 1.5 diopter. Find the focal length of the lens. Is the prescribed lens diverging or converging? So let us discuss. We know P is equal to 1 by f. P, or the power, is given as plus 1.5. So finding f is equal to 1 by p. So 1 by 1.5, we get it as 2 by 3, that is plus 0.67 meter or 67 centimeter. So since the focal length is positive 0.67 meter, it indicates that the prescribed lens is a converging lens, that is a convex lens. Question number 6. A convex lens forms a real and inverted image of a needle at a distance of 50 cm from it. Where is the needle placed in front of the convex lens if the image is equal to the size of the object? Also, find the power of the lens. So children, it's given that the size of the real inverted image is equal to the size of the object. So we know that the object must be placed at twice the focal length, or we should keep the object at 2f1. So the image will be formed at 2f2. So object distance or image distance will be twice the focal length. So here let us take the image distance. So focal length is image distance by 2 or 50 by 2. Since it is a convex lens, we can take f as positive. So we get f as positive 25 centimeter. We have to convert it in meters to substitute or give the value in the equation of power. So it is focal length is 0.25 meters. Now let us find power. Power is 1 by f, that is 1 by focal length in meters, 0.25. So by converting or by multiplying by 100 in the numerator and the denominator, we get 100 by 25. So our power is plus 4 dioptre. So children, the power of the given lens is plus 4d. Seventh question, two thin lenses of power plus 3.5 diopter and minus 2.5 diopter are placed in contact. Find the power of focal length of the lens combination. So power of combination of lenses, we can write P is equal to P1 plus P2. So P1, let us take it as plus 3.5 diopter, P2 as negative 2.5 diopter. So the combination of this lenses, the power we will get it as 1 diopter. So focal length can be found out as using the equation f is equal to 1 by p, that is 1 by 1 is 1 meter or 100 centimeter. So the focal length of this combination of lenses is 1 meter or 100 centimeter. Homework question was given to you in one of the previous modules. Please check your answer, children. The velocities of light in vacuum, flint glass and crown glass was given. Two questions. Calculate the absolute refractive indices of flint glass and crown glass. Calculate the refractive index of light going from crown glass to flint glass. So, absolute refractive index of flint glass, NF is C by VF. So, on substituting the values from the table, you get the answer as 1.61. Absolute refractive index of crown glass, NC, is C by VC. So, on substituting the values, you will get the answer as 1.52. So, here we have found the absolute refractive indices by taking the ratio of velocity of light in air or vacuum to the velocity of light in the medium. Now, the B question, we have to find the refractive index of light going from crown glass to flint glass. So, first medium is crown glass and the second medium is flint glass. So, to write the equation, NFC is equal to VF by VC. So, that is the refractive index of second medium with respect to first medium, or flint glass with respect to crown glass is equal to ratio of the velocity of light in the second medium to the first medium, that is VF by VC. So, on substituting, we get the values as 1.059. Now, the homework part. Children, 4 questions you can see here. The questions related to spherical lenses. So, please try to do it. And all the numericals except the numerical 1 along with the homework questions have to be written in the notebook. So, with this we finish this module and also the chapter Light, Reflection and Refraction. So, thank you. Revise all the modules. Stay safe. See you soon.